Welcome back to ECE 501B, large class today. Maybe they thought we had the whole week off. Is that true? So that may be the case. I apologize for missing Monday, but hopefully you were able to watch the lecture and you're still engaged with the material. This is really important material now in terms of being able to do this orthonormal decomposition of vectors. That provides us with a lot of machinery, and now we can get into some pretty fun applications of that. And in particular, the first one is minimization problems. It maybe looks a little abstract just to present it, but it's a very powerful technique. As way of announcements, homework 6 is due tomorrow, and exam number 2 is in 2 weeks. And I'm not quite sure where we will be, but we will hopefully maybe be starting chapter 7 is the plan, but we'll see how far we get today. These 3 topics pretty much finish up chapter 6, but we'll see if we can get to those in today's class. We have minimization problems, defining linear functionals. We've already worked with those really in an inner product, but linear functionals are a generalization of that, but really it allows us the opportunity to represent any linear function as a inner product, essentially. And we'll then talk about adjoints, and that allows us to look at sort of 2 different mappings. We have the normal linear mapping T, and then we will superscript that with a dagger, and that will be our adjoint operator, which will, or not an operator, linear map. It can be an operator if our 2 vector spaces that it's mapping between are the same, but it doesn't have to be. So we initially start with these 2 spaces that could be different, meaning they could be different dimensions, or they could be abstract. But for now, we'll probably be dealing mainly with the normal f to the n vector spaces. And since we are there in chapter 6, those vector spaces will be enhanced with an inner product. So we'll be dealing with inner product spaces, and we'll be then mapping between 2 inner product spaces. That will be possible using adjoints. So to start today, let's look at minimization problems, which really are a way to use what we just finished talking about in the previous lecture, the projection onto subspaces. So if you have a vector, you can decompose that vector into pieces that live or lie along these orthonormal basis vectors. And what we want to be able to do is decompose these vectors in such a way that maybe we can get close to something that's not in a particular subspace. Let's see if I can make that a little bit more clear or concise now. That was just sort of a broad brush introduction. Let's now talk about minimization problems. Again, these may look very abstract, so you may want to start putting some vectors as illustrations so that you can work through these. But it happens a lot, these minimization problems. We often, let's say, run into problems, or maybe we should say applications, run into problems that can be cast or formulated in the following way or in the following form. For example, suppose that you are given a subspace in our underlying vector space V. Suppose you're given a U and it's a subspace of V. Then we might be given a vector in our overall vector space V. What we may be asked to do then, and this is the minimization problem, is we may want to find a vector in the subspace U, a little u that's an element of the subspace U, such that the norm between the original vector and the vector in U is as small as possible or is minimized. Really what that is saying is we are trying to find a vector U that is closest, and that means in the norm that we've defined, is closest to this original vector V. And the way that we will be able to solve these minimization problems is through orthogonal projection. And that will allow us to get closest to V in this subspace U. Meaning, if you're thinking about this visually, or to try to get a mental image, you might think of the three-dimensional space and say, suppose my subspace is the xy plane, so maybe that's the floor, and now somebody gives us a vector that's not only somewhere on top of the floor, but it's also outside of the floor. It's in the height of the room. And now they want to say, okay, can you find a vector in U that's closest to that vector that's up here vertically above the floor? And if you could then orthogonally project that vector or find its shadow on the floor, that would be the U that would be the shortest. That's the idea. That's the concept, and that's what's trying to be said here. And we're going to be using orthogonal projection to make that happen. And we have just recently learned how to do that with our orthonormal vectors or basis vectors. We then will be using, or this orthogonal projection gives us just the tool to do the above, to do the minimization. And that's given to us in a proposition, as most things are in this course. Proposition 636 is the following. If U is a subspace of V, and we're given a vector V in that underlying vector space V, then what we will do is we will look at the norm of the difference between the original vector, or that vector that we were given, and its orthogonal projection onto the subspace U, and compare that with every norm between V and every other U in every other vector U in the subspace U. And what we want to do, or this is now what is true, the orthogonal projection of V onto U does minimize the distance between V and the subspace U. That's really what this is saying. So this is true for all vectors U in the subspace capital U. if we have equality between the two sides, then that's going to happen when this vector u in the subspace capital U is set equal to the orthogonal projection of V onto U. Then we will get what we want. So let's show that by a proof. Suppose we're given a U in this vector space, because we need to look at this for all U, for example. We can compute then V minus the projection of V onto the subspace U. And as always, it's probably easier to work with the norm squared. So now we have this number squared, this distance between V and V's orthogonal projection onto U. Let's just write that down again. But I can make the left-hand side less than the right-hand side if I just add a positive value to the right-hand side. And the positive value that I'm going to add is just a norm. And that norm is the projection of V onto U minus U. Now look at where these pieces actually live in terms of, if I now said, where is this as a vector and where is this as a vector? If I'm projecting, let's look at the first one on the right, the farthest one on the right. If I project V onto the subspace U and I subtract from that a U in U, where is that vector? Where does it live? This one now, I have V and I project it onto the floor. Let's say I have a three-dimensional vector and I have it holding up here in my hand. Now I project that onto the floor. So now it's at my feet. It's in the subspace U. And then I pick another U in the floor and I subtract it. Where are those two vectors when I combine them with a subtraction? Where do they live? They're on the floor. That's U, isn't it? So this piece to the far right, this is an element of U. Is that okay? Now the other one, if I have V and I subtract from that something in U, which is really the orthogonal projection of V onto U, now it's basically this vertical distance, isn't it? Or this orthogonal piece that's orthogonal to the subspace U. And I think, didn't last time we call that U perp? Didn't we define the perpendicular, the orthogonal complement, or the perpendicular to U? So this vector is in U perp. Those two vectors are now orthogonal to each other. And if they're orthogonal to each other, what do we know we can do based on a very old relationship that you learned in geometry? You can apply Pythagorean theorem, can't you? So if you said that this was, the first piece was A, that's going to be A squared. The next piece is B, that's B squared. They're going orthogonal. So now I can say that this is equal to the A plus B squared, since they're orthogonal to each other. And what's A plus B? Well, I just have this A, which is V minus P sub UV, and B is plus P sub UV minus U. So I know that this piece right here is actually just V minus P sub UV, whoops, plus p sub u v minus u squared. And this piece, or this step, was actually just the Pythagorean theorem. And I can apply that because I've already concluded that the two vectors were orthogonal to each other. Since they're orthogonal, I can take their sum and square it, and that's the hypotenuse squared, and that in a two-dimensional setting, that's equal to the horizontal and the vertical, each square. Is that okay? And now that cleans up pretty nicely, doesn't it? Since those two are equal, I can say that this black piece is still greater than or equal to the left-hand side. But now, what do I know about what I have inside the norm brackets on the right-hand side? I have a plus projection and a minus projection of a v. They cancel, and so I'm left with v minus u quantity squared. And that is what I set out to prove, that for all v's that I might, or for a v that I pick, then for all u in the subspace u, this inequality is true. And that is going to be a very useful proposition to apply in minimization problems. And I've already sort of given you a live demonstration with me holding up my hand and standing on the floor and touching a vector v, but geometrically, if I now wanted to now let me just say the geometric interpretation. And since this is a tablet that I'm sketching on, I'll just make this two-dimensional. So now suppose that V is R2. And maybe this particular line is the subspace U. Maybe my 0 or origin is down there, and now maybe my V is going off here. There's my V. Then what I need to do is I need to find that's supposed to be orthogonal, and this point right here is the orthogonal component of V, or the orthogonal projection of V onto the subspace U. That's really what we're doing. And we're just trying to make that distance between V and U as small as possible, and the smallest that we can make it is when it is orthogonal to the subspace U. That's when we get the shortest distance. This is now this piece right here is in U perp. That's orthogonal to U. And this point right here is really the closest point in U to V. And that's really our minimization problem, isn't it? If we want to minimize the distance of a vector in U to some other vector that's outside of U, then we want to find the orthogonal projection of that some other vector onto the subspace U. So solution of the general minimization problem is to actually take U equal to the orthogonal projection of V onto U. The orthogonal projection of the vector V onto U, which is really a subspace within V, that I'm just saying is contained in V. Now that we know we need the orthogonal projection, do we have the tools to make that happen? And we derived those the last time. We now know how to decompose these vector spaces, because now what do we have? We now have inner product spaces which allow us to form inner products. We have something a little bit more specific than a vector space, or we now have it a little finer in terms of what we can do with it. But earlier we saw that if we had an orthonormal basis on U, and let's say we say that that's made up of these M vectors, E1 through E sub M, then we know that the orthogonal projection of V onto U is now a bunch of inner products. It's V with E1. That gives me the scaling on the orthonormal vector E1, or in the E1 direction, plus V inner product with E2, and I just keep finding those inner products with V and these orthogonal or orthonormal basis vectors, and that's how I build up this projection of V onto U. And that actually gives us a strategy for solving these minimization problems. Our strategy, or the solution, comes down to finding an orthonormal basis on U. And how would we do that? If I give you a subspace U, how do you find an orthonormal basis on U? You need some vectors that span U, don't you? And those spanning vectors need to be linearly independent. Then, once you have that, you're not finished, are you? But you have to go back to the last lecture and use what? The Graham-Schmidt orthonormalization approach. So you start decomposing these spanning linearly independent vectors into orthonormal or orthogonal directions, and then you normalize those. That's how you now create this orthonormal basis on U. And once you have that, then you just compute all these inner products of V with respect to each of those basis vectors. So the solution comes down to finding an orthonormal basis on U and then computing inner products. And so everything's going to depend on how you've defined your inner product, isn't it? Your Gram-Schmidt depends on how you defined your inner product because that's how you orthogonalize these. The inner product tells us when something is orthogonal to something else, because then the inner product is 0. That's how we use the inner product. That's why we need to be doing this in inner product spaces. Now we have an inner product that we can play with. I don't know how many of you are reading ahead, but on page 114 of Axler, there's an example of doing just this, of doing this minimization problem. And really what he is showing is that he can get a very good approximation to sine of x with a fifth order polynomial. And it's better than the Taylor series or the power series that you normally might have used. It's much better, actually. So Axler has a great example involving finding polynomial approximation to sine of x. He's actually working in a function space, not just, I mean, his V is infinite dimensional. But all of these definitions leading up to that point, it didn't matter. As long as U, the subspace, was finite dimensional, all of these results hold. And U now is fifth order polynomials, which says what dimension is that? Do we remember? If we had x to the fifth plus something x to the fourth, then we have a coefficient on x to the 5, x to the 4, x to 3, 2, 1, and even the constant. So it's a six-dimensional space, isn't it? So with a six-dimensional U, he can get a pretty good approximation to this infinite dimensional waveform, or in function space, capital V. That actually takes place in a function space, which is where we're going in maybe the last part of this semester, infinite dimensional V's. We sort of restricted attention when we jumped into chapter 2, didn't we, of finite dimensional spaces. That was chapter 2, and that allowed us to come up with basis and spanning and linearly independent. And then we can just keep progressing, and we just keep stacking things on top. So after chapter 6, where now we're still sort of fleshing out a space again, this is now an inner product space, and what we can do with that, what do you think? Now we're going to start putting maps on top of those vectors, or inner product spaces, and that's chapter 7. And then we'll start specializing that to other cases. But we just keep sort of playing with our space. Then we start doing maps between spaces, and now we're starting to enhance the characteristics or properties of these spaces. And now we're up to an inner product space in chapter 6. Where was I? Oh. Well, maybe I should say Hopefully that example is very understandable. So now you know, I mean, in the 30 minutes that we've talked about this, this is a big thing, this minimization. Now you could go out and work a career solving minimization problems now that you have this machinery. Because you're always trying to do minimization problems. But let's keep going. Let's add a little bit more onto this. Let's look at something that we've already sort of played with, but we didn't define it formally before, maybe in this way. But now let's talk about, so I don't want you to think that just because we spent 30 minutes on minimization, it must not be that important. It's a big deal. But we didn't need a lot after we've built up this much into the semester to deal with it. Now we know how to play in that domain or in that space. Let's now look at linear functionals. Here's a description. A linear functional on a vector space V is a linear map between the vector space V and the scalars. This vector space usually has scalars associated with it, and now we're just going to map into those scalars. It could be the complex numbers, those scalars. It could be real numbers. Those are our scalars. So really that's all we're doing, and we've done that before, haven't we? We've gone from a vector space into a scalar. We just take the norm of a vector. That's sort of this way. But now what we want to do is we want to sort of pick a specific vector and form an inner product with this. If we pick a vector W that's in our vector space V, then the inner product of V with W, that would be satisfying this definition of linear functional, is a linear functional. So if I give you a vector space V, you could say, oh, I'll give you a linear functional. I'll just find a vector in V, and now you give me any other vector in V, and I'll map it to the scalars by using this inner product. W would be fixed. Maybe it's just along the x-axis if you were in 3 dimensions. That would be a valid inner product, or that would form a valid inner product, which would produce a linear functional on V. And we've been playing with this already, haven't we? We already saw this. Let's say we already saw it. Was a linear map to the scalars. That's the inner product. We just hadn't called it a linear functional. Which we could say, oh, that's a special name. So now you can go home and start talking about linear functionals and impress everybody. But you now know that that could just be an inner product. Huh? But it's a linear functional. We just didn't have a special name for it before. Now we do. Now what's surprising is that linear functional doesn't have to be starting with a vector. Well, let me just try to state it, and then we'll see how to interpret it. What's surprising is that for any linear functional, which the textbook sort of says is, let's say, a phi on V, we can actually pick a vector W in V such that that linear functional on V, that's the notation that we'll use, could actually be set equal to V inner product with W. So really, no matter what this linear functional looks like, we can actually build one up out of a special vector W in V, and then we just have to form the inner products. You give me a V in the vector space V, and I can form the inner product, and that will be equivalent to a more generic linear functional. And that's actually then given to us sort of in this theorem. So here's a theorem, 645. Given phi, which is a linear functional on V, then there is a unique vector W that's in V such that phi of U is equal to U of W for all U in V. So no matter how or where your linear functional comes from, you can actually create an equivalent linear functional, basically, out of an inner product with a vector W. And we're going to find that vector W. And that makes the process maybe easier to turn the crank. And we're going to find that basically through the proof of this theorem. Will sort of give us a proof by construction. First, let's define an orthonormal basis on our underlying vector space V. Let's now say that we have an E1 and E2, and our vector space V is n-dimensional. That's an orthonormal basis on V. Then, if we had this linear functional applied to U, then that's the same as this linear functional on, and now I'm just going to do a orthonormal decomposition of U on this orthonormal basis. And how do I do that? Well, I take the inner product of U with E1 and scale the vector E1. Then I take U with E2 and use that to scale E2, and I just keep going. So now, really, all I'm doing is doing an orthonormal decomposition of this vector u that I started with. And note that these pieces right here those are just scalars, aren't they? That's what an inner product does. It gives us scalars, and these are simply weighting these orthonormal basis vectors. That's phi of u. And now what we want to do is play with the properties of these scalars and this linear functional, etc. Meaning, the linearity of the functional allows us now to rewrite this as I can just pull out those scalars and now operate on E1 with that functional. Plus u e sub 2 phi e sub 2. This step now is the, let's say, the linearity of the functional. But now what was this functional right here? This phi, I can plug in a vector, E1, into that functional by definition of the functional. It takes a vector and produces what? A scalar. So I take the linear functional and I operate on E1. That's going to give me a scalar. Do the same thing with E2. That gives me a scalar. So now I have a bunch of scalars right here. And what I want to do now is actually bring those inside the inner product. And I actually want to put those into the second slot of each inner product term. So if this is a scalar, phi e sub 1, and I slide it into the second slot of an inner product, what happens to that scalar? Do you remember? It's going to be the complex conjugate, isn't it? If I put it in the first slot, it would just be the scalar. But I don't want it scaling u. I actually want it operating on E1. This is a vector, E1. I now want to pull that scalar inside and put it in the second slot, and now that's going to be that scalar complex conjugate. What am I saying? I'm trying to say that this is now u, and then I have phi E1 conjugate E1. Is that okay? That notation? I'm going to run out of space, so I'm going to skip the E2 one. And I now have u phi e sub n. Again, that's a scalar, and I can find its complex conjugate, e sub n. So this is now, what property was this? This was the conjugate homogeneity of the second slot. Allowed me to make that replacement of that second line with the third line. Now what do I want to do? Well, if I look at all of those pieces, I have n of those pieces, n actually inner products, but every vector in the first slot of all n of those inner products is the same. It's a u. So why don't I just pull all of those n inner products into one big inner product with the vectors in the second slot being added together? That's really all I'm doing. I'm just going to use the additivity of the second slot now and pull all of those n inner products into just one big inner product. Meaning, I'm now going to say I have u with a vector phi E1 star E1 plus phi E sub 2, again, that's just a scalar times E sub 2 plus phi E sub n conjugate, whoops, wake me up occasionally if I'm not quite all together, and I put in a curly brace, so I guess I have to close that before I close up my inner product. This line is just the additivity property of the second slot. But now what I really have, I could call that a W, couldn't I? I know my linear functional, that's phi, but I also know all of these E's. Those are my orthonormal basis vectors. So before you even give me anything, if I've now found my orthonormal basis vectors, I can compute that W, can't I? I don't need a U to compute W. I can just turn the crank and put that W together, because it just depends on the E's. Meaning I now have converted this linear functional phi sub u is now equal to u w. With the w vector actually being phi e1 conjugate e1 plus phi e2. That's the linear functional operating on e2, and that will just give me a scalar e2 all the way to phi e sub n e to the n. And that's actually a big deal. That's a big result, although it's not really stated too dramatically in the book. But I think it's the last sentence, in the last sentence on page 117 in your textbook. You'll see that, but it's kind of just buried in a paragraph. But this is a big deal. It's a part of the proof, but it's there. What has this done? This shows us that a W actually exists. What did our theorem say? Our theorem didn't say just exists, did it? It says there is a unique vector. So we've shown that a vector W exists so far in our proof. Now we need to show that that vector W is a unique vector. And the way that we sometimes do that is we say, oh, suppose it's W1, suppose it's W2, and then we'll show that W1 has to equal W2. And then it's unique. That's what we want to do. So far what we've done is we've shown that a W does exist. Is that W unique? And now let's just do what I said we were going to do. Suppose or assume that this linear functional phi sub u is equal to u w1 and it's equal to u w sub 2 for all u. But if those two inner products are equal, then their difference should give us the 0, right? It's a scalar. It should give us 0. So we can now say, okay, I can start with 0, and I can write 0 as u w1 minus u w2. And that also is for all u. That's what that upside down A means. I think I used that last time. So I'm getting lazy, not wanting to continue to write for all. So there's the for all is the upside down A. But what else does this say? Now I can just use the additivity of my second slot, can't I? The u is the same, and now I have W1 minus W2. That's for all u. Well, if it's for all u, it can be for a particular u, and I'm going to be very selective with the u that I want it to be for now. How about I consider a particular u equal to W1 minus W2. W1 and W2 are in that same space because they're in the inner product. So they have to be coming from V. So that's okay. They can be forming U. But if U is equal to W1, W2, then now I know that the inner product of U, which I'm saying in this particular case is W1 minus W2, with W1 minus W2 is equal to 0 since it was true for all U. But now I'm going to use one of the properties of the inner product. And which property am I going to use? The definiteness property, right? When the inner product is equal to 0, the only time that happens is when the vector in the argument of or in the slots of the inner product are 0. But the definiteness property of the inner product says that if I have A inner product with itself equal to 0, that's true if and only if A is equal to 0. Which says then that W1 minus W2, which is our A, is 0, which says that W1 is equal to W2. And now, not only does W exist, it's also unique. So now that theorem gives us a way of finding what we want, which is an ability to build up an inner product that replicates this linear functional or produces this linear functional. We can now create a W, and now once we have that, we can just turn the crank on this inner product with any vector you give us, V. So we're done with that proof. What have we done? We've done minimization problems. We've looked at linear functionals. Now let's look at the third thing that we were trying to talk about today, and that was adjoints. And this has a couple of different definitions in mathematics, so you kind of need to keep them straight. According to Axler, they're not really the same thing, so we'll use it in this regard in this class as an adjoint. So now the adjoint is the next topic. In order to play with this, we actually an adjoint is actually a mapping. And to make it as general as possible, let's make that mapping not just an operator, meaning it's not going to map from one space back to itself. Let's make it map between two different spaces, two different inner product spaces. And that's what we need. So to play with the adjoint now, we need two different inner product spaces. So suppose we have a T, which is a linear map between V and W. Meaning we want V to be an inner product space for any vectors in V, and we need an inner product space for vectors in the codomain. So we have a domain and a codomain again, a V and a W, and they could be different. If they're different, we need two different inner product spaces, meaning V and W are both finite dimensional inner product spaces. So I'm assuming you're going to be texting this, so you may just want to say FDIP. So V and W are FDIP spaces over this field F. I've done a lot of sort of black parentheticals here, and I just started with given a linear map, or if T. And that linear map T is mapping between V and W. Then we can actually build or create an adjoint, which we're going to represent with a dagger. Since Axler uses our symbol for complex conjugate in the book, he uses a star, and we've already used that for complex conjugate instead of a bar. So we're changing up the notation a little bit. This dagger is in contrast to Axler, who is using what we've already claimed is our complex conjugate symbol. So when you're reading the book, I don't think you'll get confused, but just pay attention that we're going to be using a dagger. And this is what we're calling the adjoint. Is this T with the dagger. And that's another linear map. Well, we haven't shown that it's linear. We'll show it's linear in a minute. So let me just say is a map now from W to V. So if we went from V to W, now the adjoint's a way to go back. And here is how it's going to be defined. Defined by, first pick a W in this inner product space, capital W, given a linear functional phi on V, such that if we computed this linear functional on V, then what we're saying is if we took the inner product of the linear map T with V, and remember T goes from V to W, so TV is in W, that's a vector in W, and the inner product needs vectors in the same domain, so TV must be inner product with this vector W. So these vectors those vectors are in W. Since, well, V is where? That's in V, isn't it? that T is a mapping from capital V to capital W, which says then that if we take TV, that's in W. Is that okay? That's what I'm trying to state here. So we now have a linear functional operating on V, and that's going to be this inner product of TV with W, and we're trying to use that to create an adjoint operator. What is TV W inner product as a result? What does that give us? If I just said, what do you get when you take a linear operator and map V through it, and then take the inner product of that with W? What's the output of an inner product? Or what's the result of an inner product? It's a scalar. So this is now a scalar. Now we want to make that equal another scalar, which is going to be defining the adjoint. So now what we want to do is create this T dagger operating on W. And remember what T dagger did. That was an operator from W to V. So T dagger W is the vector in V such that phi V, which is the linear functional on V, is actually equal to V T dagger W. And these vectors are in V. Since W is in W, but T dagger is this linear, well, we'll show it's a linear map. I haven't really said that yet, but it's W to V, which now says that T dagger W must be in V. What we're saying is that T, this linear map, and its adjoint are defined such that TVW is actually equal to V T dagger W. And one is an inner product on W, one's an inner product on V, but they both give you scalars, so we can make those scalars equal. Let's put an example to this, and maybe you can at least have something concrete to be thinking about. Right now he's going, adjoint, T dagger, T, what in the world, all these maps going back and forth. I'm not sure what's happening. So let's look at an example. And really this example should help show you how we're creating or actually building this new operator or new map. This new map, it's not yet an operator. We can restrict it to that later, but for now it's just a map that we're calling an adjoint. Now to make it interesting, let's not let T just map from V to V. Let's give us two different domain and codomain that are different. So let's just pick R3 to R2. And suppose that the linear map T takes a vector from R3 and creates a vector in R2, which let's just say it takes the second component and adds to that 3 times the third component, and that's now in our first coordinate of R2. And our second coordinate in R2, let's just say, is 2 times x1. So there is our linear map. And that's a way of taking a 3 vector to a 2 vector. We now want to create or build an adjoint, another map, but what's it going to do? So T takes us from this room to the floor, doesn't it? Now what we want is we want T dagger, or the adjoint, to take us from the floor back to the room. It's not quite the inverse. So because we don't really have an inverse, do we? Because we're going from R3 to R2, but it's a map back to the other space. So to have an inverse, we need things to be, if we were doing it with a matrix representation, that would have to be square. And here, we don't have a square matrix, do we? We're going from 3 to 2. So that's a rectangular matrix if you did a matrix representation of T. Now what we want to do is we want to go from small to big. And we kind of know injectivity, injective maps, surjective maps, etc., and those relationships. Now, what do we want? What does T need to do? Or I'm sorry, T dagger. So T dagger, what does that look like? Or what's that mapping between? We said it's taking the floor to three-dimensional space, isn't it? It's going from W to V. Now to build up, to create T dagger, let's just pick a vector in W. So to create T dagger, we pick a W in W. We were dealing with X's in V. Let's deal with Y's in W. So now we have W is Y1, Y2. Those are our two coordinates, and those are yet to be determined. We don't know what those are, or those are just given. And we need to know, how do we map Y1 in 2 space into 3 space? All right. What we want to do first is we want to say, okay, I have this expression I can build out of x's and y's as an inner product, and that's supposed to equal TV and W inner product. So if I do that, how did we create V? Well, V was in 3 space, wasn't it? So that was this vector x1, x2, x3. There's V. And T dagger, we don't know what that is yet, but that's T dagger operating on y1, y2, something in 2 space. But that's supposed to equal, by that black line up there now at the top of the page, that should equal T x1, x2, x3, or the linear map applied to a vector V in R3, inner product with W, which we've parameterized as y1, y2. But this linear map of V, we know what that is. That should take us into a 2 space, shouldn't it? T x1, x2, x3 is this guy. The first coordinate is x2 plus 3x sub 3. And the second component was 2x1. Is that okay? And now we just form, and let's just use the Euclidean inner product. What will that produce? Well, we just take the first slot, or I'm sorry, we take the first coordinate in the first slot and multiply it by the first coordinate in the second slot. And we just do that with the second coordinate, meaning we now have x2 plus 3x3 times y1 plus 2x1 times y2. Or that's x2 y1 plus 3x sub 3 y1 plus 2x1 y2. But now we know that that's supposed to equal this x1, x2, x3 times t dagger y1, y2. So now we want to form, what is it that's multiplying x1? And that's going to be our first coordinate in t dagger y1, y2. So we look at this scalar. This is now a scalar. And I was in the R's. If I wasn't in the R's, if I was in the complex, I would have had to take some complex conjugates, but I don't have to worry about that. So now I have, what is scaling x sub 1? Meaning now I'm taking something which is x, maybe I should do this, 2x1 y2 plus x sub 2 y1 plus 3x sub 3 y1. Is that okay? I've sort of ordered it x1, x2, x3, and that's supposed to be some inner product with x1, x2, x3. What do I have to put in the first coordinate of t dagger y1, y2 such that when I multiply it by x1, I end up with the necessary terms up above? Does everybody see what I'm trying to do? I need to say, well, what's scaling x1? Well, that's just 2y sub 2. So when I form the inner product in V with something over here, then I'm going to get what I need, which is this scalar. Now, what scales x sub 2? That's y1. And what scales x sub 3? 3y1. Now we know exactly what dagger is, t dagger. Now we know t dagger of y1, y2, which is this map from R2 to R3, needs to be, we take the second coordinate and we scale it by 2 and put it in the first coordinate of R3. We take the first coordinate and just plop it down into the second coordinate of R3. And the third coordinate will be 3 times the first coordinate. And that's now our adjoint map. Yes. So this is going to be unique. We may have to prove that, but maybe we won't. This is now and it's going to depend on the inner product that we've selected, but we were using the Euclidean inner product, and if somebody gave us the linear map T from before, now if somebody says build the adjoint, it's not quite the inverse, is it? Because now we take y1 and y2 and we map it into an R3. But what will it give us? It'll give us exactly the same scalar that TV gave us before. with a W. And that's what we want. That's how we're defining T dagger, or the adjoint. That it operated on W needs to, when inner product with a V, will give us the same result as TV operated on the same W. So they give us the same scalar. So they sort of play together. They play nice together, but it's not quite the inverse. But they do map between the respective spaces. T takes us from V to W, and T dagger takes us from W to V. And we'll have to pick up at that point by showing some different properties of dagger, T dagger, or the adjoint next time. But that will pretty much finish up chapter 6, hopefully next time. So you should be okay to finish up chapter 6 in terms of reading. Okay, I'll see you Monday.